Okay, in this podcast we're going to be looking at what's called reaction mechanism. And reaction mechanisms are really just steps that someone has proposed is the sequence of what happens during a chemical reaction. We often write a chemical reaction as though it's occurring all in one step, but in fact there's often elementary steps that occur. And since we can't see atoms and molecules, most of these are actually just proposed based on, let's say, chemical intuition and some reaction data. Okay. So, and the reaction mechanisms that get proposed must agree with two things. One is the overall stoichiometry of the equation and the experimentally determined rate law. So we've talked about determining the rate law, right? Based on concentration. Remember looking at those concentration tables, concentration and rate. We double one, we see what happens to the other, we determine what the exponents are and all that stuff. Those are the experimentally determined rate laws. So whatever these mechanisms are, need to agree with those and the overall stoichiometry. Okay, so let's take a look. So reactions may occur either all at one step or through several discrete steps. Each of these separate steps is known as an elementary reaction or an elementary process. And they actually use terms that describe whether how many things are actually reacting as reactants, and they call this the molecularity. And you might see these in the questions on the AP test asking about what is the molecularity of the process. So if you have just one reactant with a coefficient of 1, let's say I have something decomposing, it's going to be considered unimolecular. And my rate is going to be K times just that reactant's concentration. If I have two of the A's, I've got two things reacting, it's going to be bimolecular, and I'm going to say it's K to the concentration of A squared. It's also bimolecular if I have two different reactants. It'll be K times A times B, or the concentration of those. It is possible to have what's called termolecular, where I actually have three different things reacting, but it's really rare, and most of what we're going to see on the AP test are going to be unimolecular, and more likely even it's going to be bimolecular. So the other thing we're going to talk about in this podcast is in a multi-step process, there's always going to be one rate or one step that limits how fast the whole reaction can go. So for instance, if I look at this let's say avenue, and there are red lights along the way, in this scenario it's plaza A, or the light at A, that really slows down the whole process. So I can't really speed up the process unless I can do something to speed up what's happening at this light. In this scenario, the rate determining step, or the slow step, is going to be what's happening at plaza B. Okay, probably an even better example is we can have some relay races, and if any of you put me on your team, it doesn't really matter how fast everybody else, all the three of the others of you, run, because we're going to lose. Okay, even if my foot didn't just have surgery, we'd probably still lose. So I am, in that case, the rate determining step. You can put Alex Felix on my team, and we are still going to lose, because I will determine the rate at which that reaction completes. Okay, so the overall reaction can't go any faster than that rate determining step. We're going to talk about, as we look at some of these, two different things that sometimes are confused. One is an intermediate and the other is a catalyst. Now you can identify an intermediate because you don't start with it. It's not one of the initial reactants, and it's not one of the final products. It is something that gets produced in one step and consumed in another. So it's not there in the beginning, it's not there in the end, it's just there along the way. As opposed to a catalyst, which is there at the beginning and there at the end. Okay, it goes in at the beginning, it comes out at the end, and it still shows up in the final reaction as itself. It doesn't change in the process. All right, so let's take a look at an exercise. It says nitrogen oxide is reduced by hydrogen to give water and nitrogen according to this equation, right? And one mechanism that was proposed is to account for this reaction is this three-step process. Okay, and the question is, what is the molecularity of each of the three steps? And show that the sum of these elementary steps is net reaction. So the molecularity of this step would be bimolecular. Okay, this would be bimolecular because I've got two NOs. Here I've got two different species, one of each. This is also going to be bimolecular. Again, I've got two species, one of each. This is also going to be bimolecular. Okay, now show that the sum of these elementary steps is the net reaction. So what I have to do is look at trying to simplify this. So here I have N2O2 produced here and used here. And this cancels out. This is one of those things known as an intermediate. It gets produced in one step, consumed in the next. Okay, let's see if there's any other intermediates. Here's an intermediate. N2O is here and here. Doesn't look like there's anything else that we can cancel out. This is just like canceling things out of a series of simultaneous equation that you might do in math. All right, so let's write the overall equation. So I have still 2NO plus 2 H2s, and that gives me an N2 plus 2 waters. All right, let's see how that compares to the initial reaction. 2 NOs, 2 NOs, 2 H2s, 2 H2s, N2, and 2 H2O. Okay, so here we met that obligation 1, which is the stoic matches. Okay, the stoic matches. The overall reaction matches the sum of the elementary steps. Okay, that's what we're trying to do in that problem. Okay, so let's take a look at this equation, or this problem. It says the balance equation for the reaction of gases nitrogen dioxide and fluorine is the following. It gives us an experimentally determined rate law. On the AP frequent pre-response, you're probably going to be asked to determine the rate law, but here we're given it, and it said here's a proposed mechanism. And the question is it acceptable and does it meet the two requirements? So let's take a look. First thing we want to do is take a look at the stoichiometry, and in order to do that, what we want to do is look at, look at what we can cancel out. So if I look carefully, I see that there's a fluorine here and a fluorine here, so that's an intermediate, and I can eliminate that. It doesn't look like there's any other intermediate, so I'm left with 2NO2 plus F2 gives me 2NO2F. Okay, so let's see if that matches stoichiometry. Yes, that matches. Okay. Second thing, so it has met the first requirement, stoic, right? So now we need to see if it matches the rate law determines, the experimentally determined rate law matches the rate laws that come out of this. Okay. So one of the things we want to do when we see a slow step is we want to draw a line under that, because the rate is going to be determined by the slow step, and whatever preceded it. Nothing preceded it here, so it's just a slow step. So we're not going to add this step to the rate. So what I'm going to say is the rate is equal to some constant times, and I'm just going to call that K1 because it might be different from the K up here, NO2 concentration and the fluorine concentration. And like I said, we're not going to add the rate here because it's a fast step. And if I look at what I have here, it matches what's here. Okay, so if I have to give an answer, here is a I pasted this in because I write so slow. Alright, so we would if you were answering this on the AP exam, you could say something like this. Yes, it agrees with both the stoic and the experimentally determined rate law. And you want to go on to say that the first step is the slow step, whose rate expression is this, which matches the experimentally determined rate law. Okay? So that's the nature of the explanation you want to give. No more, no less. Okay, so most typical free response questions on kinetics on the AP exam are going to have you do the whole shebang, right? So you're going to start with maybe part A and part B, which tells you you've got this reaction. It gives you concentration rate table. You have to determine the rate law. Remember, that's again where you double the concentration of one reactant, leave the other one constant, look at what happens to the rate, determine the order, which becomes your exponent. Then you determine what the slope is, and that's your K. Remember all that? So that is your experimentally determined rate law. Okay, and then it will give you a proposed mechanism and ask you if it agrees with the experimentally determined rate law and the equation. Okay, let's take a look at what that might look like. So this would be that part. You've already done the work. You've come up with a rate, experimentally determined rate expression. Okay, and so now we want to look at this one and see if it agrees. If this mechanism that was proposed agrees with what we came up with an earlier part in the problem when we came up with the rate law. Okay, so here I've got an intermediate AB, right? And this is the slow step, so I need to put my line here. So let's just see what we got here. A plus 2B yields C plus D. Now I'm going to have some equation up here that I've done on part A or B, and I'm going to see whether or not it matches, right? It's going to match the stoic, and then it's going to match the rate expression. Okay, so this rate will be some K times A times B, right? And this rate will be some other K, let's call it K2, times B, which gives me an overall rate for the equation of rate is Ka times B squared. Okay, because I'm multiplying these together. Okay, so if this is the experimentally determined rate law that I got up here, then I would say yes, it agrees with the experimentally determined rate law. This is a slow step, so I've got to add the two together. It matches the stoic, therefore it's justified. Let's take a look at another. Alright, so here's one. Okay, so let's eliminate our intermediates. There's one, N2O2. N2O is also an intermediate. Okay, so the other thing I want to do, I usually should do this first, is draw a line under the slow step, because that's going to be where I determine my rate equation. Okay, so I have 2NO plus 2H2 give me an N2 plus 2 waters, and I've got to just see if that matches my stoic. Okay, so let's develop the rate expression here. Rate is K times this K1 times NO squared. This rate is K, let's say K2 times H2. Alright, and then my overall rate then will be some K times NO2, or NO squared times H2. Alright, so let's say I got this, and you know, the hope is that this matches the rate expression you came up with by looking at the experimental table data. If it doesn't, then you want to say it is not justified because it does not match. So even if you got the first part wrong, you can still get this part of the free response correct, get all full credit for it, as long as you answer the question based on what you came up with, right? So if it doesn't match, you say no, it's not. It doesn't match the overall experimental rate expression. Alright, so here's one where we have to prove which of the following mechanisms fits the given reaction and experimental rate law. So we're given some reaction, we're given some rate law, and we're going to compare these three and see which one matches. So if let's just see what's happening with the overall stoich in each of these and see if any of them are different that might help us eliminate something. So I can eliminate this m, so I have 2x plus y gives me z. Here I eliminate m, I get 2x plus y gives me z. Here I have n and m's being canceled, and I have 2x plus y gives me z. Okay, so all three of these equations, these overall stoichs, came out exactly the same, which may match the equation that I have. And that just goes to show you that for any given equation, there's lots of different ways you can propose mechanisms have occurred that match the stoich. But it's got to not just match the stoich, it's got to match the overall rate expression. So let's take a look. So here, at number 1, I want to draw my line here, right? Now this rate is going to be rate is some constant times x times y, right? There's nothing here, so this is overall, also the overall rate expression. Here, this is my slow step, so I want to do both of these and then combine them into one, right? This is going to be x squared. This one will be rate is y. I add these together and I get rate is some k times x squared times y. And then this one, slow step, is right here, and what I will get is rate equals some constant times y. So all three are different. All three of what I come up with are different, and hopefully one of these three will match what we came up with in the experimentally determined rate law.